All right. So we got any stragglers? Okay, we're looking good there. All right. So greetings, YouTube. Greetings, scholars. We are at the top of week 6, all right? So I think the rhythm, hopefully everyone had a good weekend and you were able to get some rest, do what you wanted to do, but also did what you needed to do. I definitely encourage a balanced work-play balance as much as possible. So with this being week 6, the rhythm that we have for the semester, basically we do 3 weeks of lecture and then 1 week of testing. We could lecture 3 weeks of lecture, 1 week of testing, so on and so on and so on. So this is the second of the 3 weeks of the second set of 3 weeks, right? So with this being week 6, what that means is during week 8, we can anticipate exam 2 to cover the information from weeks 5, 6, and 7. As always, this is remote asynchronous. So if you're in the Zoom call right now, that means you've gotten your attendance credit and you're not obligated to stay. This is College Algebra 1. So the main thing that we're responsible for is we need to be sure that we're making our way through our assignments that are on Blackboard, because that's how I monitor you guys. All right. I'll be checking the attendance again around 2:15, right? So once I do that first wave of attendance, then I'll go on with the lecture or the presentation, and then I'll check again around 2:15, right? So if you don't want to be caught in that second wave, you really want to be in the waiting room like 5 to 10 minutes before the start of class. And I do the best I can to start right at like 2 o'clock. And then that's when I start taking attendance. And so if you don't make that first wave, I don't look again until 2:15, because otherwise, if people keep trickling in, it just eats into too much of our precious time that we have together. I'm trying to think. I felt like there was something else I wanted to say, but I can't think of what it is. So we're just going to kind of continue where we left off from last time. So I think last time we did, keeps doing this. Come on. 2 o'clock is this one. So we're continuing chapter 1 from graphs and functions. Last time we did section 1.4, a library of functions. And so here, we're going to continue that discussion and take that list of library of functions and talk about transformations of functions. So I think when we were together, there were only so many of the basic functions that we did together, right? Because our time is limited. So I definitely encourage you to watch the full lectures that are on my YouTube channel. You should be subscribed to my YouTube with your notifications turned on, at least while you're my student. So that way, as I post different things, you should get a notification. And so we're going to take that list of basic functions and start doing manipulations on them. So to kind of recap, we had the identity function, which is like y equals x. We had the constant function, which is y equals a number. That's going to be a horizontal line. Y equals x, the identity function, is a diagonal line. Then you have the squaring function, y equals x squared, which is a U-shaped graph. Y equals x cubed is like an S-shaped graph through the origin. We have square root function. Square root function is like if you took the parabola, the U-shaped curve, turned it on the side to the right, and cut it in half horizontally. Square root is the top half of a sideways parabola. Absolute value is the v. And then you may have come across something that's called the greatest integer function. It's called the step function because the graph of that function is going to be, it looks like a staircase. So it's called the step function. The greatest integer function is, it's like if x is less than or equal to it's like if x is an integer, then you just take that integer. If x is less than or equal to the integer, then you take the integer to the left, that's just below it. It's a little bit detailed. It's just a random function that kind of comes out. So what we're going to do today, we're going to take that list of basic functions and talk about some transformations. So we have a few objectives with this section. We like to define transformations of graphs, use vertical or horizontal shifts to graph functions. We like to use reflections to graph functions and use stretching or compressing to graph functions. So we'll get through as many of these together as we can today. Again, with this being remote asynchronous, the real intent is for this time to be like a Q&A or a study session or office hours. I just fill it with the the lecture or I fill it with these presentations just so that there is not dead air. Because we don't have enough time to actually get through all of this together. So that's why I do my pre-recorded videos. So here we have this slide on transformations. If a new function is formed by performing certain operations on a given function f, then the graph of the new function is called a transformation of the graph of f, right? So given some original functions, we're going to be doing manipulations on them. So the first one that we want to take a look at is graphing vertical shifts. So let f of x be the absolute value of x. And then g of x is going to be the absolute value of x plus 2, and h of x is going to be the absolute value of x minus 3. We actually sketch the graph of these functions on the same coordinate plane and describe how the graph of g and h relate to the graph of f. So the basic function here is the absolute value of x. All right. Anybody know what that shape looks like? That generic shape looks like of absolute value of x? All right. So absolute value of x, the general shape is like a V, all right? So then we're gonna see, okay, so if the basic function is absolute value of x, we're gonna see what happens when we add a positive on the outside of our basic function and subtract a positive on the outside of our basic function, all right? So we're gonna see how these affect our graphs, okay? So what we're gonna do is basically make a table, all right? Choose several values of x, find the corresponding f, find the corresponding g, and find the corresponding h, and then plot these three graphs on the same plane or coordinate axis and see if we can see the difference, see the manipulation. So the suggestion is to make a table of values and graph the equations. So here, we have our x values. Let me kind of do this real quick. We have our x values that we just chose. And then we found the corresponding y. So absolute value of x for these guys. And then when we add it to, right? So absolute value of x, for instance, absolute value of -5, absolute value is the positive distance away from 0, right? So absolute value of -5 is just 5. Let's turn this back on. Absolute value of -3 is 3. Absolute value of -1 is 1, so on and so on. Absolute value of 1 is 1. So absolute value is the positive distance is a number is away from 0. So then when we look at the absolute value of x plus 2, it's like we're adding 2 to all the y values. Notice this 2 is on the outside of our basic function. So it's like we're basically adding 2 to all the y values. Adding 2, adding 2, adding 2, adding 2, right? Okay. So we're just adding 2 to our y values for this one. So then notice, can anybody describe what happened as we went from the blue to the red? How could you describe this change? All right. If the blue is our absolute value of x, notice that the vertex goes to the origin. All right. Let me see something. Okay. All right. So then when we add 2 on the outside, it causes the vertical shift 2 units upward. Right. So this says that adding a positive outside our basic function shifts our graphs up that many number of units. Okay, so adding a positive on the outside causes it to go up. What do you think happens if we subtract a positive on the outside? Which way could you anticipate it going? All right, let's see. Same deal. We have our x's. We just chose some x's. Here's the absolute value of x. When we pass those x's to the absolute value of x. And then for the next part, it's like we're subtracting 3 from every y. So we subtracted 3, subtracted 3, so on and so on. Okay. When we graph these side by side, and we can confirm that it caused our original graph to go down 3 units, right? So what this is, the thing with this section, so what this is showing is that if we add a positive number outside our basic function, it causes the original graph to go up that many number of units. If we subtract the positive on the outside of our basic function, it causes the original function to go down that many of units, right? So these are the first 2 of, I think, 8 total transformations. Yeah, I'll leave it there for now. The thing with this section is that I want to say the material is not difficult to grasp, but it is a lot of information. It can very easily create information overload, right? That's what happens to students in the past. It's not that the concepts are difficult, it's just that it's a lot of seemingly random information, all at once, right? So it definitely can have that sensation of information overload. But these are the first two transformations of 8. Right? So here's a more formal articulation of what we just said. So let C be some positive number, then the graph of f of x plus c is the graph of f of x shifted c units upward. If we say f of x minus c, it's a graph of f of x shifted c units down. All right? So again, if we add a positive on the outside, it causes our graph to go up. If we subtract a positive on the outside, it causes our graph to go down. So outside manipulations are typically vertical manipulations, and they typically follow our intuition. Let me say that one more time. Outside manipulations are generally vertical manipulations, and they follow our intuition, okay? So if that's vertical shifts and outside manipulations, then let's see what's going on here. Writing functions for horizontal shifts. So let f of x be the squaring function, x squared. G of x is going to be x minus 2 quantity squared, and h of x is going to be x plus 3 quantity squared, right? So a table of values for f, g, and h is given on the next slide. The graphs of the three functions are shown. Describe how the graphs of g and h relate to the graphs of f. So same deal, we're gonna basically make a table, plot these three functions on the same coordinate plane and compare and contrast. And so if outside manipulations cause it to go up and down, then what do you think is going to happen when we do inside manipulations? All right, let's see what happens. So here's a table. We chose several values of x. We pass it through the squaring function, and then we pass it through our additional functions, right? So when x was -4, over here, it generated 36. -3 was 25. And then with this one, it just happened, the pattern started to repeat. You see the 16 ended up here, the 9 ended up here, right? So we're going to see how that shows up in the graph. And so that's when we subtracted a positive on the inside and then added a positive on the inside. It kind of behaved in the fashion that you see on the right. Okay. So then here, we see that we have our original function x squared. Now notice, when we subtracted a 2 on the inside, your intuition may have said, oh, -2, it might go in the negative direction, but in reality, it went in the positive direction. Right? So, the x-intercept, the way I kind of remember it is what value of x makes this guy 0, right? Or what's the x-intercept here? So then when x is 2, it makes this guy 0. So the thing with inside manipulations typically cause a horizontal change, and they're the reverse of our intuition, right? Intuitively, you might think this goes in the negative x direction, but in reality, it goes to the right. So, it went to the right. See here, we added a 3 on the inside, so it's the reverse of our intuition, so it went in the negative x direction by 3. Okay. Again, the way I kind of remember it is what value of x makes this 0. So since +2 makes it 0, we went to the right by 2. -3 makes this 0, so we went to the left by 3. Right? So the inside manipulations are a little bit more nuanced than the outside manipulations. Outside manipulations, you see a positive, you go up. See a negative, you go down, right? But inside is the reverse. Okay. I feel like there should be questions. Let me pause for the calls right there. Let me just check my Zoom and see if there are any stragglers. Okay, we do have some. Man, it's like I'm always struggling. By the time I get to you guys, it gets tough. It gets just more and more tough. I just be wanting to take a nap. I'm done at this hour. Like, I don't want to talk anymore. I just want to go to sleep. I got this student and this one. Okay, let me see, let me see. I think the stream is good, so let me go like this. Okay. So if you're just joining us, we're working on the next section, which is transformations of functions. We're taking those basic functions that we have from section 1.4, doing manipulations on them to generate the graph, right? So we've gone through 4 of our at least 8 transformations. The first 2 were vertical manipulations. If we add a positive outside our basic function, it went up. We subtract a positive outside our basic function, it went down. We subtract a positive inside our basic function and went to the right, which is the reverse of our intuition. We added a positive inside, it went to the left, right? So those are the first manipulations. Outside manipulations typically cause a vertical change and they follow our intuition. Inside manipulations typically cause a horizontal change and they're the reverse of our intuition. Okay. So here where it says the graph of G is the graph of F shifted 2 units to the right. This caused it to go to the right by 2. This caused it to go 3 units to the left. Okay. So then just a more articulate way of recapping what we just said. So given C is some positive number, then the graph of F of X minus C is going to be C units to the right. And then if we said F of X plus C, is going to be C units to the left. So C unit. Totally outdated song. But that for some reason it just ran across my mind. But I think it just happened because I am sleepy. But that's neither here nor there. Let's keep going. And again, you got to stop me if I'm going too fast or if anything isn't clear, you just have to get my attention. Let me check the chat really quickly. I just checked it a moment ago. It looked good and it still looks good. Okay. So here we're asked to sketch the graph, right? So we mentioned this before. The basic function here is going to be square root of X. All right. So square root of X, we said was what? The top half of a sideways parabola. So now when we're doing multiple transformations in one function, the recommendation is like first you identify your basic function. In this case, the basic function is square root of X. Then you want to work your way from the inside to the out. So the innermost manipulation is going to be this +2. This one's inside our basic function. So inside manipulations typically cause a horizontal change and they're the reverse of our intuition. Intuitively, you might think this goes in the positive X direction +2, but in reality, this says go to the left by 2, right? Like this guy is basically, it's a sentence. It's describing to you the shape and the location. This says the shape of this graph is the top half of a sideways parabola. It's almost kind of like that shape there, right? Like this. This says the top half of a sideways parabola, and then we move it left by 2, and then we go down by 3. Let's look at that one more time. So again, this is a sentence. This is describing to you, you know, this is basically a language class. This says you start with the top half of a sideways parabola. This says to go left by 2 and then go down by 3. Okay. And then you could confirm it by, you know, making the table of values and plotting the points and confirming that it matches those transformations, right? So notice the basic function was the square root of X. Now they rewrote it as X minus, right, for the inside, but you still get your -2. This has to go left 2 and then down by 3. Down by 3. Okay. So since C was negative, the graph is shifted horizontally 2 units to the left. Okay. And then shift the graph 3 units down. So we start with the top half of a sideways parabola like you see here. Then we go left 2, this X plus 2, left 2, and then down 3. Okay. let me see the time. All right, so we've talked about 4 transformations, so now we have another set of 2. So the first of the 2 is going to be reflection in the x-axis, right? The graph of y equals negative f of x is a reflection of the graph of y equals f of x in the x-axis, right? So if we started with y equals f of x, and then we're going to finish with y equals negative f of x, it's like the y value went from positive y to negative y. So if you picture your favorite graph where it's going from positive y to negative y, we're reflecting over the x-axis. So if a point x comma y is on the graph of your original function, then the point x comma negative y is on the graph of your new function, right? So multiplying the outside of our original function caused a vertical change. It caused it to flip vertically over the x-axis again. So it's still kind of following what we said a moment ago, where outside manipulations cause a vertical change, and it flipped over the x-axis vertically. And here's an example. So if you're considering a negative on the outside, for any x comma y that you have on your original, you're also going to have, or you're going to have x comma negative y on your new graph. When you're considering, basically it's like the x value stayed the same, but the y went from positive to negative. Okay. Okay, so that was reflection in the x-axis. So now let's consider reflecting in the y-axis. So now it says the graph of f of negative x is the reflection of the graph of f of x in the y-axis. In this case, our negative is inside our basic function. Inside our basic function, right? So if we put the negative inside our basic function, then what that means is that, you know, the y values are staying the same, but it's like our x values are going from positive to negative. So if we think about our original graph, and then, you know, the y goes from the x goes from positive to negative, that's flipping horizontally over the y-axis, right? So if a point x comma y is on the graph of your original function, then the point negative x comma y is on the graph of your new function. Long story short, it's going to flip horizontally over the y-axis, right? So that's when we multiply the inside by a negative. Okay. Okay. Let's keep going. So explain how this graph can be obtained from the graph of our basic function of absolute value of x. Right. So again, when we work in multiple transformations in one go, the recommendation is to work your way from the inside to the out. Can anybody describe to me what is the shape of absolute value of x? What's that shape? And I know that you know it. What's the basic shape of absolute value of x? Okay. So that basic shape is going to be a V, all right, where the vertex is at the origin. So then if we're working our way from the inside to the out, the innermost manipulation is this guy. Can anybody tell me how will that affect the graph, right? So before we said inside manipulations typically cause a horizontal change and is the reverse of our intuition, right? So the value of x is going to make this 0 is going to be x equals 0. Sorry, x equals 2, right? So then that says if 2 is our 0, then that means we go to the right by 2. So that says to go start with the V and then go right 2 units. Okay, so if we're working our way from the inside to the out, the next one that we want to consider is this guy. So we multiplied the outside of our basic function by a negative. So multiplying the outside by a negative is like your y's go from positive y to negative y. So that's going to flip vertically. Flip vertically over the x-axis. Okay. All right. So then the last, we have this +3 on the outside that says to go up by 3. So we're going to go up 3 units. Okay. So that's what this sentence says. This is a sentence we're translating. It says to start with a V at the origin, you go 2 units to the right, you flip vertically, and then you go 3 units up. Okay, if you put all that together, you see it here. We went right by 2, I flipped it vertically, and then went up by 3. And that's the final. Okay. All right, let's see what we got. Okay. So here we ask, let me see, is this the same one? It's different. So we have f of x equals absolute value of x. Okay, all right. So I think we've discussed 6 of the at least 8 transformations that we have down the pipeline, right? So we had 2 for the vertical transformations or translations, 2 for horizontal, and then 2 for the flipping, vertically and horizontally, right? We talked about flipping vertically, we talked about flipping horizontally. So now we want to look at the transformation of stretching or compressing a function vertically. Okay, so given a function, we're going to work with the absolute value function again. And then for g, we're saying 2 times the absolute value of x, and h is a half times the absolute value of x. So notice that this 2 and this half are outside of our basic function. We're asked to sketch the graphs of f, g, and h on the same coordinate plane and describe how the graphs of g and h are related to the graph of f, right? So absolute value, I think we said was, I'm going to use this color. That's fine. Absolute value we said was a positive distance away from 0. So the absolute value of those guys is going to be 2, 1, 0, 1, and 2. Okay. So now when we do g, since the manipulation is outside, it's like multiplying each y by 2, right? So if we multiply each y by 2, we'll get 4, 2, 0, 2, 4. And then h is multiplying each y value by a half. Yeah. So half of 2 is 1, 1 half, 0, 1 half, and 1. Okay. So if we plot all of these ordered pairs, we get this, where the blue is our original. Now notice when we multiply the outside by a number larger than 1, we call this a vertical stretch. Like if you think about the blue, imagine that the blue graph was on Laffy Taffy or some kind of like putty or something. And then when you go to stretch it and elongate it, the V is going to kind of get tall and narrow, right? It gets tall and narrow. So multiplying the outside of our basic function by a number larger than 1, we call that a vertical stretch. Multiplying the outside of our basic function by a number between 0 and 1, we call that a vertical compression. So it's like it smushes. So it gets short and wide, right? So we have a vertical stretch versus a vertical compression. Okay, and that brings us to these 2 transformations. So the graph of y equals 2 times the absolute value of x is the graph of absolute value of x vertically stretched by multiplying each of the y coordinates by 2. And something similar for the 1 half is going to be our basic function vertically shrunk by multiplying each of the y coordinates by a half. Okay. So then we have vertical stretching or compressing. The graph of a times f of x is obtained from the graph of y equals f of x by multiplying the y coordinate of each point on our original function by a and leaving the x coordinate unchanged. The result is we're going to get a vertical stretch away from the x-axis if we multiply the outside by a number larger than 1. We get a vertical compression towards the x-axis if that outside number is between 0 and 1. Okay. All right. So outside by a number larger than 1 causes a vertical stretch. Outside by a number between 0 and 1 causes a vertical compression. If a is negative, first graph absolute value of a times f of x by stretching or compressing the graph vertically, then reflect the resultant graph about the x-axis, right? So if we multiply by a negative, you still do what we just did in this description, but then you flip it vertically over the x-axis. Okay. So we talked about vertical stretching or compressing. So now we want to consider horizontal stretching or compressing. The graph of y equals f of b times x is obtained from the graph of f of x by multiplying the x coordinate of each point on the graph by 1 over b and leaving the y coordinate unchanged. Right. So we still got that thing where inside manipulations cause a horizontal change and causes the reverse of our intuition. So like with the vertical, when we multiply the outside by a number larger than 1, it causes a vertical stretch. Well, the reverse is true for the inside. When we multiply the inside by a number larger than 1, instead of causing a horizontal stretch, it causes a horizontal compression. Right here. If we multiply the outside by a number larger than 1, it's going to cause a horizontal compression. If we multiply the outside by a number between 0 and 1, it causes a horizontal stretch away from the y-axis. Okay. Okay. So if our b is negative, first graph f of absolute value of b times x by stretching or compressing horizontally, and then reflect the resulting graph about the y-axis. Okay. So it says using the graph of a function y equals f of x in a figure whose equation is not given, sketch each of the following graphs, right? So if this is the graph of f on the right, this little, it looks like a hat to me with a brim, all right? All right, so let's see. So intuitively, you might be tempted to say, oh, this might cause a horizontal compression because that number is smaller than 1, but it's the reverse. So this one would cause a horizontal stretch by a factor of 2. So the x value should stay the same. Sorry, the y value should stay the same, and the x value should basically multiply them all by 2. So this one would go to like -4. I'm doing that right? Yeah, horizontal stretch. This one should cause a horizontal stretch, horizontal compression, still a horizontal compression with a flip. Okay. Let's take a look at the type notes. So stretch the graph horizontally by a factor of 2, right? So you see the 2 doubled into 4. You know, all the x's were multiplied by 2. Okay. And then I think the next one we said was a horizontal compression. So compress the graph horizontally by a factor of 1/2. So basically you cut each x value in half. You get something like this. So this one, not only do you compress it by 1/2, but now you flip it over the y-axis. Okay. So sketch the graph for this function. All right. Let's see the time. We got just under 10 minutes. Okay. So our basic function here. Can anybody identify the basic function here? What's the basic function? All right. So what this is saying, we start with a parabola. So I'm gonna call it just g for now. Our basic function is gonna be x squared. So then when we're identifying multiple transformations in one function, again, we want to work our way from the inside to the out. So the innermost manipulation is going to be this -1. So that tells us that we need to go to the right 1 unit. Okay. Next, we multiply the outside by 2, which is a number larger than 1. So it should cause a vertical change and it should follow our intuition. So we want to vertically stretch by a factor of 2. Okay. Next, we multiply the outside by this negative. So that causes it to flip vertically over the x-axis. Flip over x-axis. Okay. And then lastly, we added 3 on the outside. So adding 3 on the outside is going to cause it to go up by 3 units. Okay. All right, so we start with, and you can kind of follow the vertex. We go to the right by 1. We stretch the entire graph by a factor of 2. So it's like our x values stay the same, but the y values get double. We flip vertically, and then we go up 3. Okay. We started with a parabola. I think we said we go to the right by 1, stretch vertically by a factor of 2, flip vertically over the x-axis, and then go up by 3 units. Okay. Let's see. All right, I think I'm going to stop there because I'm burnt. Okay. So, are there any questions? Would you guys like to ask any questions before we go our separate ways? Okay. Let me go ahead and share this to Box. Nope, that's not the right folder. This one. College Algebra 1. So all the things that you see me writing, you can pull a copy of it on our Blackboard page. I think it's item number 3 is going to say daily lecture notes, Box link. You'll find a copy of these notes in there. Just the main thing is just you're making your way through our assignments, right? Do the best you can. If you're having to use a book voucher, you just have to do the best you can. You know, if there's nothing you can do right now, you know, it is what it is. But you're still going to be responsible for that material at some point. Like, you're going to be responsible for it. So, all of our assignments, you know, unlimited attempts, and that's why I kind of built it the way I did. But we get unlimited attempts. There's only a 10% late penalty, and the system is set to take your highest score. Okay. If there aren't any burning questions, we're going to end the session here. And from one beautiful mind to another, stay dangerous. Peace.